Okay, so for this video, let's turn my volume. Yeah, so for this video, just for recap, I'm going to describe the composition of blood. I'll include the components of the plasma. I'll describe the mechanism by which red blood cells are removed from the circulation. And then I'll explain how heme's broken down, what happens, the various components of the heme. Then I'll describe the three mechanisms that contribute to hemostasis, vasoconstriction, platelet aggregation, and coagulation. And then I'll give special attention to the role of platelets and the coagulation cascade. And then for the coagulation process, I'll describe intrinsic, extrinsic, and common pathways. I'll also discuss the role of TPA, plasminogen, and plasmin. So starting off, let's change colors. We'll be talking about blood. Okay, so this is going to be like a little test tube. This is our blood sample. So for centrifuge blood, spinning around super fast. It break up into three different layers. It'd be this layer here, boom, a boom, and da boom. So this bottom layer is going to be our red blood cells or erythrocytes. Erythrocytes because erythro something means red and cyte means cell. I don't know. Anyways, so this buffy layer. And this is the plasma. That's where we donate our bodies for monies. All right, so plasma is about 55% of our blood, somewhere around there. And inside plasma, we got proteins, albumin, important one because we want to maintain osmotic pressure in our blood. We've got globulins or antibodies, and we got fibrinogen which is a clotting factor. If I remember, I think it's clotting factor number 2A? No. Factor 1? Anyways, we also have electrolytes. We got ions like sodium, potassium, calcium, chloride, bicarbonate. And those all help to maintain our pH and blood osmotic pressure. Oh, sorry. Let's write these out. It's got albumin, got antibodies. We got electrolytes. I don't want to write all those out, but yeah, same ones I was talking about earlier. It's nice to spell electrolytes, but close enough. We got nutrients. We have hormones. We got gases like CO2, carbon dioxide, nitrogen gas. We also have waste products such as urea, creatinine, bilirubin, and ammonia. Okay. And then, yeah, here we have red blood cells, buffy layer. It's going to be a lot of our, 55% of it in the plasma, which are non-formed elements like we were talking about beforehand. In the buffy layer and the red blood cells, we have formed elements, which is 45%. Red blood cells, erythrocytes, their main purpose is to carry oxygen using the hemoglobin. Hemoglobin comes in two different flavors. When we're little babinos, they have these like helicopter looking things, just globular proteins. 4 subunits. In adults, it's 2 alpha, 2 beta. In Los Niños, these alternate. Oh no, my eraser hole. Okay, there we go. Anyways, I erased way too much. That was unnecessary. Alpha, beta. Okay, so yeah, that's not beta. So with Los Babinos, instead of the alpha, we have gamma. I always hate drawing out. Yeah. So yeah, we just flip that frown, turn it upside down for the babinos. That's why they're crying so much. But the difference with gamma is that they hold on to oxygen more tightly. Why? I don't know, but it just does. So this, and then we have this little, where's the thing? Laser pointer. All right, so this whole subunit right here is called a heme. Hemes are that, and at the center of each of these hemes, we have iron. And each one of these irons can hold one oxygen. So an entire subunit of hemoglobin can carry, no, I don't want that, can carry 4 oxygen. Super good. Good for the lungs. We're going to talk about that later. Not today, though. But anyways, yeah, so within our formed elements, we have hemoglobin, like we were talking about. Red blood cells, which are carrying hemoglobin. Hemoglobin's on the red blood cells. Anyways. We have white blood cells, part of our Buffy layer. If that Buffy layer is thicker than a Snicker, then more than likely the patient is very sick and it's no good to have an infection. Then we also have platelets or thrombocytes. And those suckers will help us to clot our blood if we get a little cut or something. Anyways, so we have a lot of red blood cells. We make lots of them, 4 or 5 million red blood cells per cubic centimeter. So that's a lot. A lot of red blood cells. Then if we want to hit a healthy level of hematocrit, it's about 40 to 45%, 45 million per cubic centimeter. And yeah, full of hemoglobin. So anyways, those eventually die, and as they're dying, they gotta get broken down. So inside of our spleen, we there's these little kind of net-like protrusions that will capture our disformed red blood cells. So when they get older, they get kind of deformed. They're not that pretty little jelly donut shape, or I don't know what the scientific word for it is, but they lose that. So yeah, we have these reticular fibers within the spleen, or I don't know what the name of these suckers are called, don't matter. So they get caught like a net, and they are primed to be killed. So if they're 120 days old, they lose the flexibility, and then there's going to be some macrophages eat them. That's what this is. This is our macrophage. Macrophage. And it says, ooh, num-nums. So what it does is it breaks down the red blood cell into a heme unit. And what happens here is the heme will be transferred into biliverdin. It's a bluish color. That's why, what's it called? If you get a bruise, then it's purple at first because it's kind of like purple-green kind of color. And that is our biliverdin. But it'll be transferred rather quickly by an enzyme called biliverdin reductase, and it'll change double bonds somewhere. I can't remember exactly where, but it'll change it in bilirubin. And it's yellow, but we need to make sure it's unconjugated bilirubin, because it is. Bilirubin will be transferred to our liver, so it can move freely around the blood as conjugated bilirubin in our liver. It'll put on glucuronic acid. That makes it soluble right now as bilirubin. It's lipid soluble, so it does have the ability to pass the blood barrier. But yeah. So sorry. Yeah, it can't move in the blood yet as bilirubin. So it'll tack on with albumin. It'll track the bilirubin, and then it'll take it to the liver. And then once it gets to the liver, it becomes conjugated with the glucuronic acid. And then when it gets into our colon, there's some bacteria that eat that conjugated bilirubin, and it'll be metabolized to get off that glucuronic acid, and then it'll turn it into urobilinogen, spelled like that. Oh wait, no, sorry. Yeah. So it gets conjugated, that gets the glucuronic acid taken off of it, and then if that was to be eaten more by the bacteria, it'd be turned into stercobilin, which is brown in color. I think we all know where that's going to end up. Or it can also be excreted in the urine as urobilin. Excreted in urine is a urobilin, which is yellow color. And then with the iron and whatnot, I don't think. Well, yeah, let's just talk about it. So with the iron, it'll be recycled and be transported by another membrane to the bone marrow, and then we'll recycle it unless, in the case of like a menstruating female, they'll lose that iron because they're bleeding. Then it's also stored in the liver and the spleen. It's stored in the liver and spleen, yeah. And yeah, anyways. So, another thing. Common thing that can happen is we can have a bile duct blockage because of pancreatic cancer. Or if we're a little babino and our livers aren't, as a baby, their liver isn't super, it's not working like it should because it's not fully developed. So, or if you're an alcoholic, if you have these kind of liver problems, then what can happen is that we'll have too much of the conjugated, in these cases, it'd be jaundice. In the case of pancreatic cancer, no, I don't want that. I'm just going to call it panc cancer. Cool. We have too much conjugated. These instances, there's too much of the unconjugated, so since it's yellow, that's why you can look yellow, and we call that condition jaundice. Very fun. So yeah, that's how the beams get broken down. Some of them get recycled, not a lot of them. And my stuff fell on me. Alright. So moving on from this spot, we will start talking about hemostasis, or the mechanism hemostasis. How are we gonna clot? Because we gotta clot our blood. Well, eventually. So if we're gonna draw this blood vessel, this is gonna be our basement membrane. Yeah, so that's the basement membrane. Inside of our blood, like we were talking earlier, we have these platelets. They could look like granules of rice, plasmids. That's what we call them. And there's a receptor on these plasmids or platelets, and this receptor is the GPIBVWF receptor. This is one of the receptors. So, it's a mechanoreceptor. If our Van Willebrand factor will bind, we'll have these little things. These are ligands. We call these VWFs, Van Willebrand factor. What's the word? Von Willebrand factor. That's all it's called. Von Willebrand factor. So what will happen, unless there's any mechanical action, then our plasmids will not become activated. But if we have something that, like for instance, we have damaged endothelial cells, aka cough cough, a cut. Dun dun dun. We have a cut. So we expose our collagen up here. Collagen. And if that collagen is exposed, then our plasmids combined, and then the von Willebrand factor combined, and then they get activated and they puff up. Yeah, so when they puff up, it's good stuff. So yeah, if we have any damage to endothelial cells, coronary is getting sheared off to damage the endothelium, they can bind to the exposed basement membrane, which can move to activate the platelet. Because as the blood flow is coming down this way, as it's bound, then it triggers open, and then pop. It's like a popping rice. It's like a Rice Krispie, going from rice kernel to, or green rice to like the Rice Krispie stuff. And if we're going to zoom in on these things being activated, it kind of looks like almost like dendrites. This is like a really big zoom in version of it. But it can release these granules, or it had these little vesicles on there, and inside these vesicles are little granules. And those granules come in one of three flavors. We got dense. Actually, this is one of two flavors. At least the ones that Brother Shaw went over, or at least the ones I can remember that Brother Shaw went over. So we have dense, and some of these dense ones, it could be calcium, it could be ADP, it could be PDGF, it could be factor 5, factor 8, serotonin, histamine, or it could be PF4. We also have other flavors, alpha granules, which I can't think of which one were alpha granules off the top of my head right now. But we have also other receptors that can be activated. Another one would be with ADP. We can activate our P2Y12 receptor can be activated that way. Another one is our TXA2, which is our thromboxone receptor, and that's activated with fatty acids. But if we're given a COX inhibitor, then that can stop that cascade. It blocks it, so then that can't be activated. And whatnot. So what will happen is as these suckers get activated, we'll look something like this. So we got 1, 2, 3, 4, and we'll have fibrinogen receptors are also on here. Fibrinogen receptors. Those fibrinogen receptors, one we talked about in class was GP2B and 3A. And what will happen is fibrinogen will stick the receptors together, bond two plates together. So we have a receptor right there, receptor right here, whatnot. And what that all does is that we're able to create what we call a platelet plug. So that right there is the creation of the platelet. That is not how you spell platelet whatsoever. Anyways, platelet plug. Platelet plug. All right. So, nice. And then once those granules are released, we'll recruit more, make our platelet plug. That's what we want to do. Next, we have what we can call secondary hemostasis, or the clotting cascade. So, clotting cascade will be a lot of different things. But let's say we're in the same case where we have a hole in our base membrane, our collagen is exposed. We can have a factor 12, which can hit our collagen, which will then activate factor 12a. Factor 12a can allow for factor 11. Let me scroll on my laser pointer. I gotta go back to whole. Okay, cool. So factor 11 which will cleave factor 11a. Factor 11a can do 9, which will then, so 11a will cleave 9. So 11a and cofactor 8 can be able to activate receptor 2. Receptor 2a can then be a 2, will then cleave receptor 2a, which we call thrombin. That's one of the ones that we gotta have memorized, which will allow factor 1 or fibrinogen to do its thing so that 1a, so we want to end up, which is our fibrin strands. Another option we can have is that we can just cut through the middleman, and then we'll have factor 3, which is exposed on our muscle cells up here. I didn't really draw it, but underneath our collagen we have muscles, and we got neutrophils getting ready to go into the blood at the point of an infection so they can come into the tissue. And anyways, so with factor 7, it becomes activated by factor 3. Factor 3 is just on these muscle cells, whatnot, outside the tissue. It'll become activated so that 7 will cleave into 7a, which then 7a can go on and activate 10. 10a, then we go down like we were before. So, what we call this stuff is from here all the way down until we hit... Ooh, I apologize. Right here we're supposed to have 10, which then... Yikes. Ay caramba. Ridiculous. 10, which will cleave 10a plus 5. Cofactor 5. There we go. No. Still wrong. Yeah, there we go. Okay. So, from 10 and above, we call this our extrinsic pathway, pathway. Or, that's our intrinsic, yeah. This is our intrinsic pathway. So we have damage coming from the inside. If we have damage coming from the outside, then we activate number 7. Anything from cofactor 10 down, that's what we call the common pathway, which is final clot formation. Extrinsic pathway, 7, doing its whole thing. That's fast tissue damage. It's released by damaged tissues. Tissues will react factor 3 like we talked about earlier, and they'll activate factor 10, get us back into the common pathway. Our intrinsic pathway, it's when the blood comes in contact with the collagen because we had damaged vessels. Intrinsic from the inside. And whatnot. Good stuff. So, going further in, our thrombin, will convert fibrinogen factor 1, whatnot. Cool. So, if we were talking about breaking down a clot, we have TPA. TPA, which we call tissue plasminogen activator. It'll convert our plasminogen into plasmin. And plasmin, it's a protease that's able to break down fibrin into fibrin degradation products, dissolving the clot. In this case, our fibrin strands. So our TPA is able to break it down into what we need. whatnot. Let me double check that we talked about everything. I believe we did. Cool. Till next time.